In this video, we're going to talk about isomers, specifically for our alkanes. And isomers in general are going to be compounds that have the same molecular formula, so meaning the same number of carbons and hydrogens, but different structural arrangements. So we're going to have the carbons attached in different ways to give us our isomers. So this overall process here is known as isomerism. So the specific type of isomers we're going to look at are called constitutional isomers. And this is then specifically those that are connected differently from carbon to carbon. So we have three examples here, or this is a set of isomers. If we look, all of these molecules have a chemical formula of C5H12. However, they're connected differently. So the first example here, we've got all 5 carbons connected in a continuous chain. If we look at the second example, the longest continuous chain we can find is 4. And then there is the 5th carbon coming off of the chain, so it's branched. The third example, the longest chain we have is 3. And there are then 2 of the carbons coming off of the middle, so it's kind of double branched. So again, all have the same formula, but the connectivity is different. So one thing that kind of commonly trips us up with isomers is what we know as different conformations. So conformations or conformers are when you have rotation around single bonds. So carbon-carbon single bonds do rotate freely. There's nothing holding them in place. So this example down below, we've got the 2 CH3 groups both pointing upwards, but there's nothing keeping those from spinning around in a circle. So they could both be up, we could have one up and one down, one could be over to any side at any given time. So this free rotation is not considered isomers, okay? So to go from one isomer to another, you have to actually break a carbon-carbon bond and move it somewhere else. Here, all we're doing is rotating around bonds. We're not actually breaking bonds. So this does make it a little bit tricky to see. So as an example, here is a 4-carbon chain. If I wanted to answer the question, is this an isomer? The answer is no. So even though it looks like things are moved, I have a 4-carbon chain in both examples. All I did was rotate. So I rotated around this single bond to kind of flip that last carbon down. I could have flipped it up. I could have rotated something in the middle. Right? These rotations are not isomers. Instead, we would call those conformers. So when you're looking at these, you need to really say, do I have true isomers where carbon bonds are being broken and moved around, or do I just have conformers where we're just rotating around single bonds? So let's look at some examples. And really the best way to do this is look for your longest carbon chain first. And this is going to be good practice for naming, which we will get to later in this chapter. So if I look at example A, I have 4 carbons that I can connect without picking up my pencil, so 4-carbon continuous chain. If I look at the second one in A, again I have 4 carbons that are in a continuous chain, so I can touch all 4 carbons without picking up my pencil or backtracking. So again, this is a conformer. These are conformers of each other. They are not isomers. So if I look up at my options here, I've got different conformations, so conformers of each other, just rotation. I could have isomers, constitutional isomers. So that's when we actually have bonds that are moved. And then the last option here, different compounds that are not isomers. This means usually we're going to have different formulas. So because you have to have the same formula to have either conformers or isomers, usually that's a good place to start because it's pretty easy to count carbons and hydrogens. If you have different formulas, then your answer is automatically going to be 3. So here for A, all we did was rotate, so we have number 1 as our answer. They're different conformations of the same molecule. If we look at B, We have 4 carbons, and I can hit all 4 carbons in a continuous chain. It's just rotated. Second one here, we have actually 5 carbons. So different formulas means we have different compounds that are not constitutional isomers. So the answer here is going to be 3. C, I have a 3 carbon chain with 1 carbon coming off of the middle versus a 4 carbon chain that I can hit all 4 carbons without picking up my pencil. So both have 4 carbons, everything's single bonds, so they will also have the same number of hydrogens. But the first one, I have a 3 carbon chain with a carbon coming off of the middle. Second one, I have a 4 carbon chain that does have a bend in it, but it's still a continuous chain. So here I do have isomers, and the answer is 2. Here's some more examples. The more of these you do, the better off you'll be. So if we look at the first example, we have, I can do a 3 carbon chain if I go across. I can actually get all 4 carbon chain if I go downwards. And being able to find that longest chain, again, is what's going to be helpful for naming. Okay. So I do have a 4 carbon chain with 1 carbon coming off of the second carbon. If I look at the second one, again, I can get 4 carbons in a continuous chain, and then the 5th carbon is coming off of the middle. So now the question is, are these the same thing or are they isomers? So if I number, I've got 1, 2, 3, 4 carbons, and I have that CH3 group coming off of number 2. If I number the second option, I have 1, 2, 3, 4 carbons with that CH3 again coming off of carbon 2. So because I can number and put the same group in the same spot, these are the same molecules. So we have different conformations. Things are not connected differently. We just have a rotation around the single bond. Things are flipped around a little bit. If we look at B, longest chain is going to be 4 with then a CH3 group coming off of it. Second one, again, I have a 4 carbon chain with a CH3 group coming off of it. So let's see if we can number to give ourselves the same numbering pattern. So I can do 1, 2, 3, 4 with CH3 coming off of number 2. If I do left to right on the next one, my CH3 would come off of number 3, but there's nothing stopping me from numbering the other direction. Okay, so again, that CH3 group I can have coming off of number 2. So these again are going to be the same molecules or just different conformations. We look at C. The longest chain is actually a 5 carbon chain. So I can get 5 carbons continuous if I go down that bend. Then I've got a CH3 group coming off of the middle somewhere. If I look at the next one, the longest chain I can get in any direction is 4. Then I have 2 CH3 groups coming off of it. So they do have the same formula. They both have 6 carbons. But in the first example, I have a 5 carbon chain with 1 CH3. And the second example, I have a 4 carbon chain with 2 CH3s. So these are considered constitutional isomers. Same formula, things are connected differently. Last example, we have 6 carbons in a continuous chain for the first one. The second one, we have only 5 carbons, so 3 in a chain plus 2 coming off. So different formulas means we have an answer of 3. Different compounds that are not constitutional isomers. This example is going to have you drawing constitutional isomers, and it does ask for all. So sometimes the questions just might say draw 2 or 3. The specific question wants us to draw all of them. So if you're asked to draw all of them, especially, it's best to try to do this in some kind of pattern so that you're not skipping, missing, duplicating, and so on. If you're just asked to draw a couple, just make sure you're not drawing the same thing as conformers with rotation rather than actually moving things around. So then the more different you can make them, the better. But here, the first one says C5H12. So I'm going to draw these as skeletal structures. I think it's easiest to see. So there's my 5 carbons. With everything being single bonds, I know it'll fill in properly with those 12 hydrogens. Now, in a problem, if you're not asked to draw your structures using a specific type of structural formula, then you can use whichever one you prefer. But do read the question carefully and make sure it's not asking for a specific type of structure. So I'm always going to start off with the longest chain. So there's the C5. Then I'm going to go down to only 4 carbons, so one less in my chain. And that leaves me with 1 carbon. Now, if I try to put that on the end, if I look, I still have a 5 carbon continuous chain. All I did was essentially rotate. So that is not an isomer. All right. So whenever you're going down a step, you have to make sure that you don't ever put your remaining group on the end. So if I try to put it on the second carbon, now I see I cannot have anything longer than a 4 carbon chain, and I do then have a CH3 group coming off of that chain. So here's 2 isomers. I'm going to try another 4 carbon chain. What if I put it on this carbon? It looks to be different, but if I number things, I have 1, 2, 3, 4 with that carbon coming off of number 2. And I'll see I can do 1, 2, 3, 4 on this one as well with carbon coming off of number 2. So again, these would be conformers. Things are just flipped around or rotated, so they are not isomers. So I can get rid of that option. So there's nothing else I can do with the C4 chain. Just to show you one more thing that is not an isomer, if I flip this upwards, again, it's just rotated. So whenever you cannot come up with another option with the chain length that you're working on, move down to the next chain length. So I'm going to work my way down to 3 carbons in my chain. I can't put any on the ends because that will just make my chain longer. What if I put both of them on the middle? And in this way, I'm making a 2 carbon chain. If I look carefully, I notice by doing that, I actually just made a 4 carbon chain again, which I just determined I have all my 4 carbon chains done. So this is just a conformer of the previous one. So that's not possible. What if I put the 2 carbons on the middle carbon, but both attached directly to that middle carbon? Now my longest chain is 3, and I have the 2 carbons coming off the middle. So this is also another isomer. It's the only thing I can do with 3. I can't go down to 2 because then I will automatically be putting something on the end, extending my chain. So once you get to this point, you have drawn all of your isomers. If there's nothing else and you're starting to repeat, you probably have all of them. So C5H12 has those 3 options. The next one has C6H14. So again, I'm going to start off with 6 carbons in a continuous chain. Your continuous chain options, there's only going to be 1. So I'm going to jump down to 5 carbons next. Leaves me with 1 carbon. I can't put it on either end because that will extend to 6. So I'm going to put it on the second one first. If I move into the 3rd carbon, it's still different than the previous one because I can't number them the same. If I try to move 1 step over, now I'll see I just recreated my second structure because I can number and put that carbon branch on number 2 in both. So that's not an isomer, so I'm going to get rid of it. And now that I've repeated myself as I'm working down the chain, I know I'm done with the 5 carbon chains. So I'm going to go down to a 4 carbon chain. I now have 2 carbons left. I can't put 2 in a single chain off of the second one because now I've just recreated a 5 carbon chain. If I do it on the next carbon over, again, recreated a 5 carbon chain. If I put 2 on the second carbon, but both directly attached, now no matter which way I count my longest chain, I come up with 4. So it is going to be different. I don't have a 5 carbon chain. If I put 1 on each of the middle carbons, again, longest chain in any direction is going to be 4, and this is still numbered differently than the previous one. Now eventually you'll get to the point where you're just going to keep coming up with repeats. So that's going to be the last 4-carbon chain option. If I try to go down to 3, that leaves me with 3. There's no way I can add 3 carbons without making my chain longer. So even if I tried to do something like this, now I'm back to having a 4-carbon chain, and I've just redrawn something I already had. So here are your options for C6H14. Now I'm unlikely to ask you to draw all isomers on a quiz. I will more than likely ask you to draw 1 or 2 sets. So just make sure you can draw several that do not repeat themselves. Here's a few more examples, this time using line angle structures. So just giving you practice looking at the different types of structures. So go ahead and pause the video and see if you can decide if these are different conformations, constitutional isomers, or different compounds that are not constitutional isomers. All right, so again, best thing you need to do is try to find your longest carbon chain. And the longest carbon chain I can find on this left one is going to be 5 carbons. I can also find a 5-carbon chain in the second one. And I see that I have 2 separate CH3 groups coming off of my 5-carbon chain. So now I'm going to see if I can number it and get the same numbering pattern. So if I do 1, 2, 3, 4, 5, I've got those CH3 groups on 2 and 3. If I number this one, I can also get those CH2 groups on 2 and 3. So these are the same as each other, meaning different compounds that are, no, I'm sorry, meaning they're conformers, number 1. Things are just rotated around. So at first glance, they look very different, but they are not.